Hi, and welcome to 8.7a Conservation of Energy 1. In this lesson, students will be able to apply the law of conservation of energy to different situations in an effort to calculate unknown variables. So, critical thinking. Can an object have more than one kind of energy at the same time? What are some examples that you can think of? Pause the video and think of a example where you could have more than one type of energy at the same time. Pause the video. Think about it. I have two examples that I can think about right now. A roller coaster, okay? These people on this roller coaster are having the time of their life right now, and they have gravitational potential energy because they are a height above the ground, and they have kinetic energy because they are moving. So the check is, are you a height above the ground? Yes. So that means you have GPE. Are you moving? Yes. So that means you have kinetic energy. Okay. What about this situation? Okay. We have a pole vaulter. What type of energy does this pole vaulter have? Multiple energies at the same time. What type? Well, you could tell they're a height above the ground, so that means they have GPE. Yes, GPE, gravitational potential energy. This person is moving. They have some velocity, so they have kinetic energy. What other type of energy do you think there might be in this situation? I forgot. I actually forgot to give you the check on the lesson, I'm realizing, but the check for elastic potential energy, EPE, is something being stretched or compressed. Doesn't necessarily have to be a spring, but if something is being stretched or compressed and is going to like snap back to the equilibrium position, in this case for the pole, the equilibrium position is just it being straight. That's when it's the happiest, okay? But this person is bending the pole and storing some elastic potential energy in the pole. So there's actually all three of the types of energy that we learned about in class in this very instant right here. Now, as the instant moves forward, maybe the person is gonna, yeah, it looks like they're gonna gain gravitational potential energy. I don't know. Are they going to gain some kinetic energy? That looks like the pole's gonna like kind of snap them to the top. Maybe they'll get faster a little bit before they slow down at the maximum height. But what happens to the elastic potential energy? It looks like this thing is fully bent, and then it's going to straighten out. So the elastic potential energy is going to go down in this situation. And I guess we could do the same thing for the roller coaster. Like, what happens to the gravitational potential energy? They're going to go down the hill, so that decreases. But what happens to their kinetic energy? They're going to go faster. So there always has to be some kind of balancing going on. The total energy has to remain the same. So when you add these two values together at the top and then at the bottom, the total energy is the same, even though it might transform from potential to kinetic. And that's basically the law of conservation of energy. The total energy is the sum of all the forms of energy present in a system. So this is the formula. The total energy is equal to the potential energy plus the kinetic energy plus Q. That's what they give you in the reference table. Q, remember, is internal energy or heat. Most of the time, that's due to friction. Now, there is a whole other backstory of conservative forces and non-conservative forces, and friction would be considered a non-conservative force, basically taking energy out of the system. All right, but that's all you really need to know about conservative and non-conservative for now. All right, while we're talking about the conservation of energy in the system, the total energy remains the same. So, do they give you that nice little formula? Yes, they do. It's on the back page and it looks like this. Okay, so ET is phoning home. ET is the total energy, the total energy. Very good. And keep in mind, this is the mechanical energy, right? The potential energy and kinetic energy are mechanical, and the potential energy can include gravitational potential energy and the elastic potential energy. That's both included in that PE term. So here's a formal slide, because I know you want to write this down in your notebook. It says the total energy of a system remains constant, although energy may transform into another form. In other words, energy can neither be created nor destroyed. Very true. This can be represented mathematically as the total energy in the initial condition is equal to the total energy at the end. Now, it might go from kinetic to potential, but the total, when you add all the different types of energy up, is going to be the same. So I just have one example for you, and then we're done. So it says, because we already know all the different types of energy, now we just have to apply it to, and it's going to be a bunch of different situations. In this case, a 5-kilogram ball is released from a height of 2 meters, slides down a frictionless ramp, and compresses a spring with a spring constant of 20 newtons per meter. So the question here is, what is the gravitational potential energy of the ball in the position shown? So let's do that. We have the mass is 5 kilograms. The gravitational field strength is 9.8 newtons per kilogram or meters per second squared, either one. The height is going to be 2 meters. And we want to know what is the gravitational potential energy. So this is our formula, mgh. You substitute in, and the total energy, GPE, is equal to 98. What are the units? Joules. Okay, so this ball has 98 joules of energy that it can play with. It could get transferred into kinetic energy. It could even be transferred into elastic potential energy in the spring. But because it's only 2 meters tall, and because it's only 5 kilograms, and because the gravitational field strength is 9.8, like if it was a stronger gravitational field, you'd have more energy to work with. All right, we have 98 joules to work with. If you wanted more energy, you could lift it up a little bit higher, and then it would go even faster, and then it would even compress the spring even more. But since we only have 98 joules of energy to play with, that's fine. Now, if it was like, if you throw the ball down, like let's say we want to give it some initial velocity in the y direction instead of just dropping it, then you'd have to calculate, okay, what is the initial kinetic energy if you did have some initial velocity here? All right, and then the total energy of the system would be this kinetic energy, because if you were going to throw it downward, plus this 98 joules of gravitational potential energy. All right, if you had some initial kinetic plus the height, the GPE, then it would give you a higher total energy. But we're not going to do that. We're just going to drop the ball. So that means that we only have 98 joules of energy. All right, so what is the velocity of the ball in the position shown? At first glance, you might be like, I don't really know, because I guess I should do like a kinematic equation or something like that. I'm not really sure. Let's use the fact that we know the total energy of the system and the fact that we know at this position shown here, it's no longer a height above the ground. So we can do our nice formula that was on the previous slide. It says the total energy in the beginning is equal to the total energy at the end. And then I had alluded to this in a previous lesson. Technically, you got to do KE plus GPE plus, KE plus just the potential energy in general plus Q initially is equal to KE plus PE plus Q. All right. Was there kinetic energy in the beginning? No, that's 0. Is there friction? No, that's 0. Is there kinetic energy at the end? Yes. Is there potential energy at the end? No, because it's no longer a height above the ground, so there's no more potential energy. Is there friction? No. So what we're left with is a formula that looks like this. The potential energy in the beginning is equal to the kinetic energy at the end. So we had our first, this is the initial condition, this is the final condition right before it compresses the spring. So we have to pick 2 points in time in our system, and we use that to analyze what is the initial and the final over there. So we already know that this is equal to 98 joules. We had 98 joules to work with. That's equal to 1/2 mv squared. Actually, I should write let's make the nice. So we can plug in now. 98 is equal to 1/2 times the mass times the velocity squared. And now we have one equation, one unknown. You divide 98 by 2.5 and take the square root, and you get a velocity of 6.3 meters per second. Sweet. So we just used the idea that you can use the conservation of energy to determine how fast an object moves if you know what the mass and the height and the gravitational field strength is in the beginning. You could figure out what the final velocity is going to be. Now, I was nice. I could have said, oh, what is the velocity of the ball at the point shown here? All right. Then you would have to say, okay, well, how high above the ground is this ball? Okay, so then you'd have to plug in, this wouldn't be 0 anymore. You'd have to plug in GPE here, and you'd have another term plus MGH that you would have to figure out. This is like the final height, like a different height. This is HF. So just giving you like a sneak peek of what this might look like, you would still wind up with one equation, one unknown. They would have to tell you what the height is that they want you to analyze and say how fast is it going when it's maybe 1 meter above the ground. But that's, and then it would be slower, right? You would have a smaller velocity. Just to show you like what you can do with the conservation of energy formula. But let's move on. So now we want to know how far has the spring been compressed. We know in the beginning the GPE, really the total energy was equal to 98 joules. And we want to know what the compression was. So we can do the same thing as we did before. The total energy in the beginning, that's over here, is equal to the total energy at the end. That's over here. Now it's fully compressed, so think about how fast that ball is moving when it's at the fully compressed position. The ball compressed it this way, and it's about to start turning back. The spring is going to push it back this way, but it's not yet. All right, so it's turning around. So what is the velocity of the ball at this point? The velocity at this very instant is 0 meters per second for a split second, because remember, it's turning, it's going this way and turning around, just like those problems where we were throwing the ball upward in the air. So the kinetic energy in the beginning plus the potential energy in the beginning plus Q is equal to the kinetic energy at the end plus the potential energy at the end plus Q final. All right, so again, there was no kinetic energy in the beginning. There was no friction. And at the end, there's no kinetic energy. There's elastic potential energy, but again, there's no friction. So GPE, the potential energy in the beginning was all GPE, is equal to, we should say GPE initial is equal to the elastic potential energy, EPE, at the end. Okay, so you have these different types of energy. We already calculated MGH is equal to 98 joules. So that's equal to 1/2 kx squared. Now they did tell you that K was equal to 20 newtons per meter. So I don't want to get points off for units. So I'll actually write my units in here. 98 joules is equal to 1/2 20 newtons per meter times the x squared. We want to know how much distance it was stretched, okay? So, and they could have even said, like, how far was this stretched when the velocity was only maybe like 1 meter per second? And then you'd have to put that term in there as well. But you know enough information for this to calculate what that kinetic energy is when it's 1 meter per second, and that would reduce the distance that it was compressed. But we want to know when it's fully compressed, that's where the kinetic energy is 0 because you stop moving for a split second. Anyway, so you do the calculation. 98 divided by 10, 1/2 of 20, and then you take the square root of that, and you get x is equal to 3.1 meters. That's a long spring, but yeah, that's what it is. It's a long spring, 3.1 meters of compression. Okay, maybe it's a crazy spring. I mean, a 5 kilogram ball, that's pretty massive as well from a height of 2 meters. And then the spring constant is like not, I've seen bigger spring constants than that, so it would compress it a lot. Okay. Oh, how about this one? If the ramp wasn't frictionless and the spring only had 90 joules of elastic potential energy when compressed, how much energy was transferred into internal energy or heat? All right, what is the heat there? So we need to figure out some stuff. All right, so what would you do in this situation? I'm going to erase what I just wrote so we could basically do the same thing, but it's different now. And I actually realized you might have been screaming at your screen, Mr. Nangle, it's QI initial over there. That was my bad. I did that by mistake. All right. You might already know in your gut what the answer is, but I'm going to continue to use this formula just so we know that it still works. You don't have to rely on your gut. Sometimes it's a good thing to rely on your gut, but it's good to have a backup of like things that make sense, like with math. So let's do the same process. In the beginning, there was no kinetic energy. We were not moving. There was potential energy. Now, in the beginning, there was no heat yet. It didn't go down the ramp yet. All right, the ball was over here. And then as soon as it starts going down the ramp and compressing the spring and interacting with everything, then there's going to be some internal energy that's building up. But in the beginning, it's 0. That's how you work that. Okay, in the beginning, it's just at rest. So it's not, there's no friction there. All right. At the position shown, just like on the previous one, there's no kinetic energy because the spring is fully compressed. Speaking of that, there is potential energy because the spring is fully compressed. And now they tell you, oh, there is friction, and how much internal energy is that? What they're really looking for is QF. They're saying QF is equal to what? Please tell us. All right. So GPE is equal to 98 joules in the beginning. All right, you have 98 joules to play with. Then the problem tells you that 90 joules of that, it has 90 joules right here. All right, so there's 90 joules of potential energy at the end, plus whatever leftover internal energy there is. So this is what I was saying before with your gut. Like if you could kind of visualize this maybe in a different way in your head, they're saying, well, I had 98 in the beginning. I know there's 90. The remainder must be the internal energy. It's really, it boils down to it being that simple. All you do is subtract from both sides. This is where I say like, well, I like to rely on the math and let the math tell me what to do. Because that way I don't have to guess. And let's make it nice because this is a good one. And then QF, what is that total internal energy at the end? It's going to be 8 joules of internal energy. All right, so this is just a snapshot. This is one example where you could analyze the thing at different places, but there's a plethora of different examples where you would need to apply this seemingly simple formula. You just have to keep your wits about you and do those checks. Is it moving? Do I need to put a kinetic energy term in there at either point, right? It changes. It'll change from point to point. Is it moving? Is it a height above the ground? Is it compressing or stretching a spring or other thing? Is there friction? That's like some, that'll be like the higher problems. Those will be like the starred ones at the end, or maybe I'll try to throw in something else with friction. Most of the time it's going to be energy transfer between kinetic energy, gravitational potential energy, or elastic potential energy, and the energy will go from one to the other, and you'll have to figure it out given the information in the problem. But you can handle each scenario. It'll be different, but there'll be enough information there for you to figure it out. Anyway, that's about it. Thanks for watching and have a great day.